This lesson deals with Supplemental Problem 12.3. You can find this problem in the ECE202 ebook in the Chapter 12 Supplemental Problems, starting on page 7. Can you show for the general form of a second-order low-pass filter that the magnitude is equal to H0 Q0 when omega equals omega naught? And can you further show that if the magnitude has a maximum, it has a value equal to H0 Q0 divided by the square root of 1 minus 1 over 4 Q0 squared, and that that's approximately H0 Q0 when Q is large, and that this occurs at a frequency omega equal to omega naught times the square root of 1 minus 1 over 2 Q0 squared, and that this is also approximately equal to omega naught when you have a large value of Q0. Well, to show this, we need to know what the equation for our transfer function is, so let's go back to our Chapter 12 notes and find f of s for a low-pass second-order filter. And the gain is equal to H0 omega naught squared over s squared plus omega naught over Q0 s plus omega naught squared. The magnitude is the magnitude of the numerator and the magnitude of the denominator. Magnitude of the numerator is just real, so that's going to be H0 omega naught squared. And the denominator, we plug in s equals j omega. This is going to be a minus omega squared, and that's real. And our other real term is omega naught squared. So we're going to take the real part and then square it. The imaginary part, this is going to be j omega, is going to be equal to omega times omega naught over Q0. And then we're going to square that and then square root. Now in our problem, it says to show that this equation is equal to H0 Q0 when omega equals omega naught. So when omega equals omega naught, this term cancels, and I have the square root of quantity squared, so that cancels. And then when omega equal to omega naught, that becomes omega naught squared, and that's going to cancel with this. And then this is 1 over Q0, that comes up in the numerator as Q0 times H0. So we show that this is equal to H0 times Q0. Now, if a maximum exists, we could use the second derivative test to find it. And the first step in the process of that is to find the first derivative, set it equal to 0, and then find the critical frequencies, and then we'll take a second derivative and determine whether we have a maximum or not. Let's write this expression as a product of two terms, H0 omega naught squared times the denominator raised to the minus 1/2 power. Then we can use the chain rule to find the derivative. Just got a scalar out in front, so that's still here. Then they're going to have a minus 1/2, and then that quantity raised to the minus 1/2 minus 1, which is minus 3/2. And I'll take the derivative of what's inside the square brackets with respect to omega. That's going to be 0. And we'll have a minus 2 times 2 omega to the 2 minus 1 times omega naught squared. That's this term. The derivative of this with respect to omega is going to be 4 omega to the 4 minus 1, which is equal to omega cubed. And then this term, we could pull out the omega squared. We have a constant, omega naught over Q naught, quantity squared. And then the omega squared derivative is going to be 2 times omega to the 2 minus 1, which is this term here. Now, this term is in the denominator, and this is in the numerator, and it's just a constant. So for this equation to be equal to 0, the denominator would have to be equal to infinity, and that's not possible. Or this numerator term is equal to 0. So let's investigate this one. I have a common omega to each term, so let's divide through by omega. I have a minus 4 omega naught squared, 4 omega squared, and then 2 omega naught over Q naught quantity squared, dividing that term out. Leave this on one side of the equation and put these others on the other side, so that means a plus 4 omega naught squared, and then a minus 2, the quantity squared. Next, let's divide through by 4, so I'll have a 1 times omega naught squared, and then minus 2 over 4, which is a half, omega naught over Q naught quantity squared. Pull out a common omega naught squared. I have just a 1, a minus 1 over 2 Q naught squared. Take the square root of both sides of the equation, and I get then omega is equal to omega naught times the square root of 1 minus 1 over 2 Q naught squared. Now this quantity in the radical needs to be positive, and that implies that Q naught squared is greater than a half. In other words, Q naught has to be greater than 1 over the square root of 2. If there's a maximum or minimum or point of inflection, it has to be at this frequency. In Chapter 12 on page 25, we looked at plotting the magnitude of a form 8, which is part of our transfer function for a low pass. And we saw that when Q0 was 1 or greater, that a maximum existed. From our derivation on the last page, we showed that there was one critical frequency, and that was when Q0 was greater than 0.707. If a maximum does occur, it's at this frequency. We really could skip the second derivative of the second derivative test, since we already found the frequency where a maximum would exist. Now, if Q0 is 1 or greater, then squaring it's going to make this a small number, and we're going to be approaching omega equal to omega naught. Now let's plug in this equation into our transfer function. So here's where we had omega squared, and likewise over here omega squared. Inside here I've got an omega naught squared and 1 over here canceling. Then I've got the product of these two, which gives me a plus omega naught squared over 2 Q naught squared. I'm going to square that quantity. So I get omega naught to the 4th over 4 Q naught to the 4th. Likewise over here, I'm going to put these two together, get an omega naught to the 4th. Let's bring the Q naught squared inside. So I've got 1 over Q naught squared and then 1 over 2 Q naught to the 4th. Now let's pull out an omega naught to the 4th. So when you bring that out, that's going to be an omega naught squared. That's going to cancel with this term. I'm left with, inside the radical, 1 over q naught squared, and then I have 1 over 2 q naught to the fourth, and then I've got a plus 1 over 4 q naught to the fourth. So you could write this as 2 over 4, so it's negative, and I'll be adding a positive 1 over 4. I get a negative 1 over 4 q naught to the fourth. Okay, now pull out a q naught squared. You square root that, so you get a q naught, and that goes up in the numerator. I'm left with just a 1, and then 1 over 4 q naught squared. And that's our formula. If q naught is greater than 1, then squaring it's going to be a smaller number, and this is going to be approaching h naught times q naught. And roughly at the frequency, omega equals to omega naught. What's shown here is a sketch of the magnitude of f sub low pass versus frequency. Go back to the transfer function on the previous page. Looking at the transfer function in s, when the magnitude of s is very small, then the numerator, which is not a function of s, is h naught times omega naught squared, and the denominator has an s squared term, which is going to get small, something times s, which is also going to get small, and then omega naught squared. So as the frequency gets lower, we approach h naught. Now, as you go higher in frequency, we eventually approach a slope of minus 40 dB per decade from the form 8 denominator. And then we just shown that at roughly omega naught, there's a peak for large values of q that's equal to h naught q naught. More specifically, it's equal to this anytime you have a q greater than 0.707. The distance between these two, since this is in dB, 20 log of h naught times q naught, and you could write that as 20 log base 10 of h naught plus 20 log base 10 of q naught, and this is just the h naught term. The difference then is the value of q naught in dB. This is similar to the picture on page 27 if I drew it for q less than 1, just underneath the asymptote. Do the same thing for the high pass filter, you find a very similar result. This is supplemental problem 12.3.